Last but not least, so the name of the paper is Automated Material Selection based on detected construction progress. The presenter is Tyler Stephens from Pennsylvania State University. So when you're ready, you can share your screen, and the floor is yours.
Can you hear me?
Yeah, I can hear you too.
All right, awesome. All right, so can you still see it?
Yes, perfect.
Okay, all right. So thank you. Yes, my name is Tyler Stevens, and thank you for attending my presentation on automated material selection based on detected construction progress. I developed this research with Austin McClymonds, Dr. Robert Light, and my advisor, Dr. Alan Wagner at the Pennsylvania State University. So as part of this, our objective for this research was to develop an automated robotic system that was capable of performing 3 tasks. Those tasks are to recognize the current state of a construction project, predict which materials will be needed to perform further construction.
Just to stop you 1 second, could you make it full screen? Because now I can.
Oh, it's sharing the wrong.
Yeah,
okay,
yeah,
I'm sorry.
Yeah. That's all right.
Geez, I don't know why it would do this. Yeah, I apologize. It's projecting onto my extended screen right now.
No worries.
Geez. Here. There's one solution to this. Just unplug the extra screen. I apologize. All right. Can you still see it?
Yeah, that's better.
Okay. So, as I was saying, our objective was to develop an automated robotic system that would be capable of performing the following tasks. Those are to recognize the current state of a construction project, and then predict which materials will be needed to provide further construction progress, and then lastly, deliver those materials to the appropriate work faces. This research focuses on the first 2 parts, that is steps A and B. And so therefore our objective was to develop a system that would be capable of selecting materials for staging based on detected construction progress. So this research was motivated by in order to both reduce waste as well as to improve construction efficiency and safety. The inefficiencies in construction often occur due to equipment not being available for construction workers as they're trying to deliver materials to their work faces. Workers delivering materials by hand, if the materials are heavy, this can increase risk of slipping and tripping accidents. As well as human mistakes can also be made while handling and transporting materials, resulting in materials being damaged or wasted. Related work in this area, normally work focusing on looking at construction progress normally focuses on the task of automated construction monitoring. And so this typically involves taking a BIM and comparing it to a sort of as built model developed using sensor data. These sensors can be laser scans or images, and this comparison can be performed using neural networks or probabilistic approaches. But all these methods typically focus on simply monitoring and documenting variations in progress, as opposed to trying to develop inputs for a robot to deliver these materials. And so we want to use these existing methods to develop instructions for a robot to deliver materials. However, a lot of these methods also lack the granularity needed to develop instructions for a robot. So the system we developed has 3 inputs. It uses images captured of a construction site, a BIM, and a linear construction plan. 2 things worth noting are that our BIM assumes more granularity in a BIM than is normally provided. Because our experiments focus on masonry tasks, we have provided the locations of all the blocks within the BIM. The linear construction plan is a very detailed sequence of activities that is assumed to be linear. So there would be like a step 1 to place blocks 1 through 3, a step 2 to place blocks 4 through 6, and so on. And those steps have to be performed in that order. So once we have these inputs, we take the BIM and we discretize it into an as-planned voxel grid, whose purpose is to be compared with the as-built point cloud generated from the images. And during the comparison, for each voxel in this voxel grid, we label each voxel according to its visibility and its occupancy. With this label voxel grid, we are then able to determine the probability of that the current construction progress is some state. So looking at this graph, we start in the top right corner and we determine the probability that the construction site is on the very last step of the plan. And if the probability is below some threshold, we move on to the next previous step and so on until we find a construction state whose probability is above this threshold. And so therefore we say the next step in construction and the next materials that need to be delivered are the next step. So to evaluate this system, we conducted experiments in both simulation and in real life. These experiments consisted of an array of cameras and a sort of mock construction site. Part of the objective was to assess this system's ability to determine the correct current step and select the materials for staging regardless of what the true current state of construction was. So we fully varied what the current state was across both plans for these structures. And then for the experiments conducted in real life, we also varied the lighting conditions by varying the time as well as the location of the camera around the structure. The results we collected from these experiments showed that our system was successful under all situations except when occlusions were present. If you look at the very bottom row of this table, you can see that the number of mistaken steps, the number of steps that were mistakenly determined when occlusions were present in simulation were 2. So all reconstructions that were performed resulted in the wrong step being determined when occlusions were present. However, for all the other situations, the correct step was determined. Another interesting result we observed was that in the afternoon on the second row, the probabilities collected were consistently higher than the other times, being in the morning and in the evening. So diving into these results further, you can see on the left here in the physical experiment, in this example image, the left wall on this block corner is more shaded than the one on the right, and so therefore resulted in a poor reconstruction and lower probability and occupancy in the voxel grids. The correct current state and materials were still selected, however, it did reduce the probability. And then on the right, in simulation, you can see on the left image that there's a leg occluding some of the bricks in the image, and this occlusion resulted in the voxels not being occupied after reconstruction, and so some of the construction elements or blocks were not detected, resulting in the wrong materials being selected. And so in conclusion, we believe that this system can serve as a template for future development. The material selection system was shown to be robust to lighting, but susceptible to occlusions. This system is capable of selecting materials for future progress, and so we believe it can be built upon with other existing progress monitoring systems. For future work, we aim to address some limitations, mainly that this system assumes a linear construction plan, which isn't representative of a true construction schedule. The system also struggles with scalability, depending on the number of images collected and the size of the structure, and the size of the plan. The amount of time required can vary from a few minutes to several hours. The robustness of the system, it's also not, it's not robust enough to be used on a true construction site with the amount of variation in lighting and occlusions that will be present. And for current work, we're investigating how images collected, their distance from a structure and their spacing and number might affect the material selection results. And then we're also automating the alignment process of aligning the as-built and the as-planned models. And so with that, I'd like to thank you again and ask if there are any questions.
Thank you, Taylor. Yeah, thanks. Great presentation. And any questions from the audience? No. Wait 1 second. Someone typed in the chat.
Yeah, I see the question, okay. Why the Jetson Nano was used. Yeah, so the camera that we were using to collect the images is called a Z2i camera from Stereolabs. And to use it, it requires an NVIDIA, it requires a computer with an NVIDIA GPU that supports CUDA. And so that's why we use the Jetson Nano, so that we could use this camera, because this camera has stereo capabilities that we did not use, but it is pre-calibrated. So we didn't have to perform any sort of pre-calibration on it either, but that's why we use the Jetson Nano, so that we could use the camera we had.
Hi, Tyler. This is Varun from IIT Madras. My research area is similar to this. I work on computer vision-based construction progress monitoring. I am just curious about how much time it took to process just this part of the structure, the wall part.
So it depends on which structure we're talking about. As different resolutions of images and you know, obviously these structures are very different, this wall corner versus the simulation one. But the processing time in simulation normally took about 5 minutes, as only 4 images were captured per reconstruction. For the real life experiments though, just for that simple block wall, it took about 15 minutes for the progress to be detected. And that's not accounting for the reconstruction time either. The amount of time total for this system to run would be in simulation would be more like 10 minutes, and then for the physical experiments that were performed, because more images were captured, would have been more like 35 minutes. And as I said, a lot of these, it depends on, and so this is why it wouldn't, you know, work well for a true construction site. And some optimizations, some changes to the code have been made since this has been run, using multi-processing and multi-threading. But I think a different code base is needed in order for the system to truly be usable. Currently, it's all written in Python. A faster language like C++ or something would probably benefit it.
Thanks, Taylor. Yeah, we've run out of time, and then maybe you can exchange in the private chat also. Yeah, yeah, thank you very much, Taylor, for the presentation and really interesting research. Yeah. Okay, so that will
Thank you.
be the thanks. That will be the end of the session. And yeah, thanks for having me. And I wish everyone have a good time. And yeah, also have a nice weekend. So okay, thank you very much.